we talked about equilibria and the law of mass action. And that's what your assignment is all about. This should be fairly straightforward. If I give you any equation whatsoever, you should be able to write an equilibrium expression for me. So I'm just going to make an equation up. Let's say lithium bromide dissolves in water. Well, no, that's boring. Let's do a double displacement reaction. We'll say lithium bromide reacts with, we'll say lithium sulfate reacts with calcium bromide to produce what? Double displacement reaction. These are going to switch partners, so we'll get what as our products? Bless you. Lithium bromide and how much? And what? And calcium sulfate. All right, that's going to be a solid, and that will be aqueous, and that's going to be aqueous, and that's going to be aqueous. Okay, so there it is. Is it balanced? She's real close. In front of? Oh, you're good. Very good. All right. And then we'll say this actually exists, and this is true, in a state of dynamic equilibrium. So, which means at some point, not only will lithium sulfite react with calcium bromide, but to some extent, lithium bromide will react with calcium sulfate. Now, as it happens, this is an equilibrium that is heavily favored to the right. This is a reaction that you get a lot more of this at equilibrium than that, but it still is an equilibrium. What would the equilibrium equation, the law of mass action, be for this reaction? Write an equilibrium expression for this reaction. Good, so let's pause for a second. They all start with K equals. Sometimes they use KQ, sometimes they use KC, sometimes they use KRXN. They could call this K double displacement, whatever you want. I'm just going to put EQ for equilibrium. But this is really just an identifier. It's telling you, it's trying to give you a sense of what you're talking about. And in this case, KEQ equals what?
The concentration of lithium bromide squared.
Yep. Yep.
And then over Li2SO4 multiplied, or concentration of that.
Yep.
Multiply the concentration of SCH4U.
Very good. We put the products on the top. We put the reactants on the bottom. Everything is multiplied. And where do you get the exponents? From the number of moles, from the coefficients. Good. Is that reasonably comfortable? And if I told you all of these concentrations at equilibrium, could you solve for KEQ? If I told you KEQ and 3 of these, could you solve for the remaining 4th one? Why did I circle them like that? Quiet. Quiet. It was a beautiful circling job. If I gave you all of that, could you solve for the missing one? Yeah. And it's as simple as, like any equation, you have to know everything but one thing to find a missing thing. Does that make sense? So this assignment package, sometimes I give you KEQ, I give you that, I give you that, I give you that, but I don't give you lithium bromide. Another time, I might give you all of this and say solve for KEQ. Right? Does that make sense? By the way, this only stays the same. This is only constant if what can change an equilibrium constant? In other words, concentrations can make an equilibrium shift, but what else can make an equilibrium shift? Conditions, specifically temperature and pressure. Does that make sense? Cool. All right. Okay, so that's pretty good. That's called the law of mass action. That lets us write equilibrium expressions. Now, knowing that, let's take a look at today's lesson, because today we're just going to say, okay, if I change an equilibrium, what actually happens? And today's lesson, we're for sure going to go over at least twice. Might be a 3-timer kind of thing, because this is where, for the first time in chemistry, I'm going to say the math gets a little tricky. Just a little, but we're going to meet our friend X. We're going to throw a variable into this guy. We're going to have to do a little bit of algebra. Not a ton, okay, I promise. This isn't like an advanced functions class, but you are going to do a little bit of like grade 10 and 11 math, which for some of us has been a long time, right? Like for some of you, when's the last time before data management you had a math class in person? Could have been a long time, right? Yeah, you know what I mean? So listen, I am fully expecting that we're going to have to spend a bit of time on this. I don't want you to panic, because you know what we're going to spend on it? Some time. Last unit, we had some topics that you guys had to spend some time on, and you all did great, like really, really well. By the time we got to test time, you guys all knew your stuff, and I was most impressed. All right, we're going to do the same thing this time. We're just going to keep at it till we're good at it. All right, do you trust me? Just say yes. Excellent. That was good. That sounded very convincing. You're convinced, right? No. Shut up. Okay, let's go. So let's take a look at this. We can use something called an ICE table to determine the equilibrium state of a reaction. This tool helps us keep track of information. So for a lot of reactions, you can just go online and you can look up the equilibrium constant or whatever. In this case, we're going to find Keq. Does that make sense? So here's what I want to do. This table, ICE initial, what's it start at? How does it change? What does equilibrium look like? Helps us go from starting conditions until we reach equilibrium. Does that make sense? Because we said that at first reactions happen, right? And then eventually they reach a state where the forwards reaches the backwards and they all meet equilibrium. Does that make sense? Okay. So what we're going to say is, let's see if we can figure out what equilibrium looks like. So, first things first, if we look at this reaction, how many species are involved total? Where are the 4? Sorry? Oh, sure. The 2 is a number, it's a coefficient, but it's related to the species hydrogen iodide. Just 3. Very good. So we have hydrogen iodide, which is a gas. That, by the way, is our reactant. And then what are the 2 products? Very good. Hydrogen gas and iodine gas. Or if you're a monster, iodine. Yeah, people say that. Not this guy. And if you wanted to put the 2 here to kind of remind yourself that there's a 2 on it, that's fine. I usually don't. I usually just put the title. But I've found that some people really like to remind themselves to basically make this match the equation. In fact, some people will even put kind of the equation symbols on the borders. And you may find that to be a useful habit of mind. I'm actually, for this first one, going to show you that because I found that that's something that students sort of find helpful, to just write this very much as the equation. Does that make sense? Okay. Now, I want you to imagine that this reaction starts off with only the hydrogen iodide. Now, is it yet in its equilibrium state if when we start off all we have is hydrogen iodide? Yep. No. That was Marissa Wallace, right? Okay. See, I heard that one. I don't know why I heard that one. Maybe it's like, is somebody in this room normally a heavy breather and when they're in here it distracts? Is there like some sort of weird destructive interference going on?
Preston.
I do blame Preston. I'm prepared to blame Preston really for all of my problems. Fighting with the wife, Preston. Hurt my foot, Preston. Got a rust spot on my car, friggin' Preston. Like, just I'm prepared, all of it. Anyway, all right, let's go.
I think you'll go back and watch this note.
I hope he does. This is a good way of testing. What if I just said something horrific about each of the people who listened here today, and then I would know if they watched it when they came and were like, I can't believe you said that about me. James, I question your value system. Who else is here? Tashante, your fashion choices are actually excellent. I can't even pretend. You just always look astonishingly fashionable. Well, you're better at guitar than me, and it makes me feel jealous. I don't know. This is not turning into a very effective roast session. No. Turns out the only person I can say anything negative about is Preston. Anyway, moving on. So, when we start off, all we have is this. In fact, we know how much of this we have. When we say initial, we mean when we start off, what are the concentrations? And when we start off, what's the concentration of HI here?
0.1 mole.
Very good. We're just given that in the question. The question tells us that we started this off by putting that there. Okay. And it tells us also, equally specifically, what? Which means what numbers can I put here? What other information does the question give me? Eventually, I want to know Keq, but all I know is I started off with this, and then what else do I know?
Equilibrium is 0.078 moles per liter.
Of what?
HI.
So I can take that information and I can put it here. Do I have any other information given to me by the question? No. But this is enough information. It is, I promise. So let's talk about that. Well, it all has to do with putting a bit of calculus in what we do. Now, we're not going to do it as calculus. We're going to do it with a table. Just a table. We're just going to make a table, and we're going to look at it. But the idea is to go from the initial state to the equilibrium state, this concentration had to change. Did it go up or did it go down? So it went down, and you could do the math in your head right now, but I actually don't want you to. Not yet. We will. But we know it went down by some number. And the reason I don't want you to do this math in your head right now is because we're going to follow the same process every time, even if we don't know this number. We might know a different number. Does that make sense? The point is, if we started out with nothing but HI, this had to go down by some number. So, do I want to write down by some number? Well, I could, and that's fine. In fact, I'm going to say down by some number. But then I'm going to point out that in math, how would we say this went down by some number? Well, to say it went down, we would have to say subtract. And if we don't know the number, we would... Sure, or just some number. In math, how do we say, some number, a number, something? Yeah, don't fight it. X. Down by some number. So this went down by X. And in fact, we're going to come back to this in a moment, but we're going to, well, we'll come back to it. Because, while this concentration is going down, what is happening to these concentrations? These are going up. Is there a relationship between how much this number goes down and how much these numbers go up? If this went down by 20, how much would this go up by each? If this went down by 20, how much would that go up by? Sorry? I know, but I'm just trying to get a principle here. I want to work with nice round numbers. This would go up by, and this would go up by. Cool. If this went down by 8, how much would this have to go up by? 4, and 4. Because we look and we see the mole ratio here tells me that I'm using 2 of these up to make 1 of those. So I'm going to go ahead back here, and I'm going to sneak a 2 in there. And the reason I'm going to sneak that 2 in there, and I'm actually going to rewrite it because that sucked. I'm going to sneak the 2 in there because if I use the coefficient, then I won't end up with any fractions. Does that make sense? Because this goes up by half as much as that went down. Does that make sense? Which I'm not even going to bother writing. I'm just going to say if that went down by 2x, this went up by x. And if you want to write 1x, if that helps clarify, nothing wrong with that. And what about I2? It's going to go up by x. So just be aware that from initial conditions, these are going to change. Now, here's the nice thing. Say you screwed up and say you called this plus 2x. That's okay. As long as you made these minus, you'd still get an answer. You'd just get a negative value for x, and then you'd know, oh, plus a negative is going down and minus negative is going up. It wouldn't matter, but here's what's important. The signs have to oppose each other. Does that make sense? If you've made the products positive, that's fine. Then the reactants have to be. And if you've made the reactants positive, which I would never do because to me that's weird because I think of reactants being used up. But if you're a freak of nature and you decide to make your reactants positive, and I'm joking because sometimes it actually does make sense. If your reactants are positive, then we're going to make the products negative. What's important is products and reactants should have opposite signs. Does that make sense? Now, in this case, can we solve for x? Well, we actually have a bit of an equation here, don't we? What equation do we have there? So I'm going to say 1. We can solve for x here. And the reason we can solve for x is because we know that we started out with how much? Yep. And we subtracted 2x, and what did we end up with? Very good. And you know what that is? That's an equation. So let's write it as an equation. We can say 0.100 molar minus 2x equals... I stand chastised. All right. Now, if you can just do this in your head, if you're just like, okay, that went down by 0.022, and then since that's 2x, it must be 0.011. If this is mental, if doing this as mental math for you is quicker, cool, that's fine. I'm going to do it as algebra. How would I solve for x here? Sorry? I could do, but x is, my instinct would be to say negative 2x equals 0.078 molar minus 0.100 molar. And then to get the x by itself, I can just divide both sides by negative 2, right? And I would get x is equal to 0.078 molar minus 0.100 molar divided by negative 2, and I can solve for that. By the way, I would probably never in my life show all of those algebraic steps again. You know what I mean? And can I tell you something else? We're chemistry students here. So if you find this math complicated, you could also throw that into Wolfram Alpha and just let solve for you. Do you guys know about Wolfram Alpha? It's my hero. You could also throw it into Desmos. Throw that into Desmos. Oh, do I love Desmos. You know what the best invention of the 2000s is?
Wolfram Alpha.
No, Minecraft. Do you know what the second best invention of the 2000s is? Yes, correct. Seriously, Minecraft is magnificent. It's a wonderful thing. 0.1 minus 2x equals 0.078. And you might be like, it didn't solve anything for me. But it did. Because look here. See how no matter where I scroll, that line is the answer. What's the answer? No matter what? 0.011. Hey, you just solved for x. That's cool. Look at my brackets. X is always 0.011. So at Desmos is cool because you can just plug everything in so easily, but you do have to kind of like know to click on the line to see the answer. On the other hand, if you go to Wolfram Alpha, well, we love Wolfram Alpha because I can say 0.1 minus 2x equals 0.078. I can do that, and boom, it'll just solve it for me. See that? Isn't that beautiful? Listen, do I want you to practice your algebra? Yes. Do I want you to be good at algebra? Yes. Is this an algebra class? No. Now, will you be a better chemistry student if you're good at algebra? Yeah, but I would recommend checking your work every time with Wolfram because it won't let you down. Okay. So anyway, if you plug this into your calculator, you're going to get 0.078 minus 0.1 divided by -2, and we're going to get 0.011. Now, the nice thing is, that makes solving for this really easy, because what is 0 plus 0.011 molar? Yeah. Does that make sense? Just to show you, if you do initial plus change, you always get equilibrium. Initial plus change equals equilibrium. However, it started out plus whatever the change is going to equal the equilibrium. If you were to go back and try this, it would make sense. What's 0.100 minus 2 times 0.011? 0.078. Initial plus change equals equilibrium. That's how we came up with this equation. And that's how we quickly solved these. Does anyone want me to show where this number comes from? Or are you okay? You're comfy. Like that one there. You're comfy with 0 plus 0.011 equals 0.011. I'm not saying that to be funny or anything. Like, I'm serious. This takes some processing. It's a new way of thinking. Can we stop and talk about what this means before we move on? Okay. What we've said here is that, quiet, we had some hydrogen iodide gas. And we started out with exactly 0.100 molar of it. Maybe I weighed it out, maybe I measured it out, maybe I had it in a balloon, whatever. I knew how much I had. Does that make sense? And then we provide the catalyst or whatever, we let the reaction start happening. Does that make sense? Before we let the reaction started happening, did I have any of the products? No. Now, once the reaction gets going, I must have some device that can measure this. Could be a colorimeter, could be an ionization gas detector, could be anything, but I've got something that measures this. Does that make sense? And it's changing, and it's changing, and it's changing, and it's changing, it's changing, and all of a sudden, it settles down. It picks a value and just kind of stays there. Can you picture that? When the concentration stops changing, we know that we've reached a state of equilibrium. Does that feel all right? Cool. Well, then what I said is, okay, well, from here to there represents a change. And because of the chemical equation, I know that that's going to drop at double the rate that those things get made. So to make my life easy, I'm going to say that goes down by 2x. It goes down by some amount, and that amount is double what those are going to grow by, then I can quickly figure that number out. Maybe I just do it intuitively. Maybe I go, okay, well, 0.10 minus 0.078, that's 0.022. Oh, but if that's double the rate, then kind of the baseline rate is 0.011. That's if you're kind of just a natural kind of ratio thinker. That might occur to you, which is great. Nothing wrong with doing the math in your head. Does anyone kind of think like that's the way my instinct is to look at this? That's cool. If it's not, what makes the table nice is just you can always fill this middle out. Because where do you get the change values from? They just come from the equation. The equation tells us that this is a reactant, so it's going to get used up. In math, how do we say something's getting used up? We subtract. And how many of them get used up? 2. So this will be negative 2x. This, on the other hand, isn't getting used up, it's getting made. In math, how do we say you're getting more of something? You add. How many of them do we get every time? Just 1. So plus 1x. Reasonable? And then the iodine, same thing. It's a product, so it adds. There's only one of them, plus 1x. And then just fill the information in that you know. In this case, we know we start at 0.10 and 0. We know we end at 0.078. And you can then just use algebra to solve the rest of the table. Does that make sense? And I don't care how you show it. All right? I don't care if you show it as algebraic equations, or if you say I eyeballed it, or frankly, if you throw it into Wolfram Alpha, though I think you should try the algebra first, because we will get to things where you're going to have to at least be able to set the algebra up before you can throw it into something to solve. Does that make sense? So try the algebra. And by the way, if anyone wants just algebra worksheets, my goal is to make some tonight. In fact, I might even turn tomorrow. Can I ask this? Does anyone feel like they would benefit from a day where we just practice some algebra? I got one back there. That's good. So maybe we'll just do that. Like, that's time well spent. Because, again, you guys have not had nearly as much in-person math time as you deserve. Not nearly as much time with the teacher just staying there saying, here's an equation that sucks, solve for x. Here's an equation that sucks, solve for b. Here's an equation that sucks more than the first two sucked, solve for q. Here's an equation that sucks more than all three of those, solve it for everything. First solve it for x, then solve it for y, then solve it for z, then solve it for t, then solve it for q. You know what I mean? And you just do that for weeks, it becomes second nature. You don't have to think about it anymore. And it's like anything else. I always say that, when I have to go somewhere and sing and play guitar, you can't think about both at once. If you're thinking about playing the guitar, and all of a sudden you start thinking about singing, the guitar playing just screws up and stops. You can't think about them both. One has to be on autopilot. And in doing science, it is really helpful if algebra is autopilot for you. You know what I mean? If you can just be like, oh yeah, rearrange and solve, boom, that's going to make your life easier. Is that fair? All right, now, we haven't actually answered the question. What we have done first is we have filled out our ICE table, and that should always be your first goal. Your first goal should be, as much as you possibly can, fill out your ICE table. And then, if there's anything missing from your ICE table, go down and figure it out so you can fill out the rest of your ICE table. Does that make sense? In this case, to get these two values, I had to know x. So what did we do down here? We went and solved for x. But I still haven't answered the question, because the actual question in front of us is to determine the equilibrium constant. But now I know all of the equilibrium concentrations. And if I know the equilibrium concentrations, can I solve for Keq? Let's write a Keq expression. So for this particular reaction, we're going to set up Keq and solve. So you have the reaction in front of you more readily than I do, but we can say Keq equals what? Always a fraction.
Concentration of hydrogen gas times the concentration of iodine gas over the concentration of hydrogen iodide.
There's one error in there. What's the error? Very good. And that was very good to begin with. Does that feel all right for people? How's that? Remember setting this up? Once we've set that up, solving it in this case is... Hi. And now we can solve for this because do we know the equilibrium concentrations? As it happens, we do. What is the equilibrium concentration of H2? Very good. What's the equilibrium concentration of I2? Great. And of HI? And what do I need to make sure I remember to do with that? Square it. That should be a capital K. And we can just plug that into our calculator. Though, listen, guys, you got to be careful, calculator users. Brackets. When in doubt, brackets. I'm going to put everything in the top in brackets. But see how the top gets its entire bracket open to close? I'm going to divide, and the bottom gets its own bracket. Because otherwise you run the risk of squaring the wrong thing. This one actually wouldn't not work. But once you have two things in the bottom, it's just easy to screw up. Be careful, calculator users. And you know what I highly recommend? Oh, that should only be one, shouldn't it? Sorry about that. I also put two equal signs, so you know. And we get 1.988. Did you get the same? So let's see if I'm right. Because again, I find these kinds of calculators clunky. But you know what's a great calculator? The second greatest invention of the 21st century. Yeah, because you know what I love about Desmos? When you make a fraction in Desmos, it's just a fraction. And then we can go 0.011. Oh, I forgot my zeros here. That is your problem. You got 0.01988. Yep. See, this is why we check things. And in Desmos, it is so nice and easy to set things up and it looks like math. Like, look how nice and clean that looks. It looks just like what you put on your page. Even if you don't use Desmos Graphing Calculator, have you guys used Desmos Scientific Calculator before? It's just this. But again, it's wonderful. It also, can I show you something else? You can also declare things. Like if you want to, you could say the concentration of H2 is 0.011. The concentration of I2 is equal to 0.011. And the concentration of HI is equal to 0.078. And then you could say Keq equals concentration of H2 times the concentration of I2 divided by the concentration of HI squared. And then you can change these numbers. Like it is, can't say enough good things, right? Like being able to define variables and then just use the variables as you go, life-changing. Oh yeah, it's the best. When I taught physics last year, I would make all of my solution sets just inside a Desmos file. I'd make one Desmos file, make a folder for each one, and then you could just follow the algebra right along and see how the math was done. Anyway, so we have a number, I'm going to call that 1.99 times 10 to the negative 3. We actually only have two sig figs, don't we? So it's going to be 0.020. So 2.0 times 10 to the negative 2. Right? Yeah. 2.0 times 10 to the negative 2. Yeah. And there's no units. That's right. This is a unitless Keq, which will not always be true. Or will it? Nope, it will not always be true, but sometimes it will be true. That's right, we have. Just had to think. And that's how we use an ICE table. Now, that is a fairly simplistic example, but that's okay. That's okay. This tool can be used for a lot of different things. We're going to spend a lot of days working out. We're going to do one more example today, and we're going to chill out. All right, and you can work on your assignment. We can just relax. Tomorrow we'll try some more, okay? Does that feel reasonably all right? Would you tell me if it didn't? I know there's only 4 of you, but does anyone feel like I have no idea what we just did? Okay, that's encouraging. I like that. I like to hear that. Let's try another one. In the first example, we solved for Keq. Now, here's the thing. Most reactions, you can look up their Keq. Most equilibria, I should say. Most reactions that form equilibria, you can look up their equilibrium constants, which means often we know Keq, and instead we can say, this is the much more common case, okay, what's going to happen to this at equilibrium? So here's a reaction that we can do at 700 Kelvin. This is a standard industrial reaction. In this particular case, it is oxidizing carbon monoxide to form carbon dioxide. And in the process, what does it produce? Hydrogen gas. So this can eliminate a waste product and give us a useful product, which is easy to separate by mass because hydrogen is a very light gas. Carbon dioxide is a heavy gas. Nice and easy. Okay, great. We know the Keq. Let's start just by writing an equilibrium expression. Never a bad idea. I actually should have started with that on the last question too. This is always a good place to start. Look at me. If you're on a test and you don't know what to do, you know what you should do? No, don't cry. You can be like my friend Amanda in first year chemistry. I'm sure I've discussed this with you, but
Actually, I don't think you have.
in my first year chem exam, somebody broke into the prof's office 2 days before the exam and stole a copy. I think thinking it would be too late to print new ones. But let me tell you, it was not too late to print new ones, and they wrote a very, very, very hard exam that like the best of us got like 35% on. And that's fine. They put a bell curve on it. Do you know about the bell curve? Yeah, they basically just took this, and like if that median was like 31%, they just said, oh, we're going to call that 70% now, and then we were all cool. That's all good. But at the time when we were writing it, they didn't know they were going to do that. So it's just like, what am I looking at? It was very overwhelming. And while we were writing it, my friend Amanda was sitting behind me, and she and I were very, very close friends. We worked together and we went to school together. And all of a sudden I heard, and Amanda's like, tough. She's tough. I'm the wuss in the relationship. And I was like, Amanda, settle down. It's fine. We're going to be fine. And then all of a sudden she's like ugly sobbing behind me. But it was so distracting. And I was like, shut up. Just shut up. We all find it hard. What, you think you're the only person in this gym who is feeling lost right now? Is that what you think? Settle down. Anyway, we got into a big fight in the middle of an exam. It was great. Proctor had to come over and tell us to be quiet. Yes, which when you say it that way sounds really bad.
It is so bad.
No, but you don't understand. It doesn't help. We all want to cry. Listen, can I tell you something? A fact about people. You walk anywhere in the world at any moment you want, and 50% of the people are one sideways look away from breaking down in tears. But it doesn't help. There's a time and a place, all right? Cry after the exam.
She's bawling her eyes up. She's understanding. Just shut up.
When the exam is done, cry all night long. That's fine. But you know what? If the airplane's going down, I want my pilot to be landing it, not sobbing about it, all right? If my surgery is going sideways, I want the surgeon to be figuring it out. All right? You can cry later. Right now, like, no, and I'll tell you something else. My wife talks about this all the time because my wife's a very emotional person. She'd be the first person to tell you that. But she always says that, like, she's had a few obstetrical emergencies, like where a baby is born and it is flat. And that isn't actually that uncommon. It's, believe it or not, about 10% of babies are born with vitals that need resuscitation. And usually, you bag them, you give them a little bit of air, they start breathing, everything's fine. So, like, that's pretty normal. But she's had babies where, like, they're bagging it, nothing's happening. Now it's been 10 seconds, 20 seconds, 30 seconds, and all of a sudden she's got to resuscitate. And she said, every time this happens, like, this icy calm comes over her, which, again, does not sound like the woman I've married, icy calm. And she just does the job. And she says, every midwife describes the same thing, and every doctor she knows too, where like you go through this thing and you save this life, and you do it very calmly and collectedly and just as if it's business as usual. And then she's like, and then as soon as you get a minute to get out of the room, you like go to the bathroom and like vomit and break down sobbing. Because there's a time and a place. That's all I'm saying. So, dear Amanda, who is one of my beloved best friends, let's all fail this exam first, then we can cry about it. It's the order of operations. Anyway, yeah. So Gerhard the proctor had to come over and be like, guys, you're being a distraction. It's like, sorry, Gerhard. Anyway, what's the Keq expression for this reaction? Very good. Very good. Now, I note you have no exponents. Is that right? Should there be no exponents?
Correct.
Yeah, how'd you know that?
There's only 1 mole for everything.
Very good. Yeah, so all these have to be first-order interactions. There's only 1 mole of everything. Good. Okay, with that in mind, we can start filling out our ICE table. And again, I recommend, not a terrible idea, especially when you're starting off, to kind of just rewrite this as your equation. So what do we start with in this first box? Concentration of? Yeah, obviously you could do water as well, but we might as well match it in the same order as the question. We're just writing all of our reactants in here. We're setting up our ICE table. And what we're saying is that as this reaction goes on, we're going to track the concentration of each species involved. And this reaction is a bit more complex than the last one. The last one only had 3 species. This has 4. But that's okay. That's cool. We can do that. So what is the initial concentration of everything? Do we know? Initial concentrations. Do we have any? Yeah, start with means initial, right? So 1 mole of carbon monoxide gas. And you might say moles per liter, though, Orlando. It's in a 5-liter solution. So can we turn that into a concentration if we feel so inclined? Yeah. What's 1 mole in 5 liters? Oh, you know what? I picked all gas. Can I tell you something? That says solution, but it should say container. This isn't an aqueous solution. It's a container, but that's okay. We can still say 1.0 moles in 5 liters. And what will that equal? Very good. So 0.20 molar. We're going to assume that 5 is exact, precise. And the nice thing is the next one is actually the exact same calculation. So how much water do we have? 0.20 moles per liter. All right. And we're going to assume when we begin that we have no products. Unless we're told otherwise, that's a fair assumption. Okay, what can we do here? We're given the equilibrium constant, but we do know the change. We know how they're going to change because the reaction tells us how they're going to change. And the reaction tells us what? What gets used and what gets made? Sure, so how am I going to indicate that these get used?
Negative X.
Yeah, and I'm not even going to put X's there yet. We're going to say those get used, so those are being subtracted away. On the other hand, these get made. How am I going to indicate that?
Plus.
Yeah, in other words, we know that these are going down, and as these are going down, these are going up. Does that feel all right? Now, you're right, we don't know the number, but we know that whatever the numbers are, this is going down at exactly the same rate that is going down. Does that make sense? because the reaction tells us that for every one of those we use, we're also going to use one of these. And it tells us that we're going to make one of those, and we're going to make one of those. So whatever the change is, it's actually, in this case, all the exact same number. Does that make sense? Because it's a 1 to 1 to 1 to 1 mole ratio, I actually missed a 1 there, they're all the same number. This goes down by something. But this goes down by the same something. However much this goes down by the same. And however much these have gone down, that's how much these go up. That's the beauty of a chemical equation. It gives us a lot of information. So this is worth noting. The C row, the change row, always comes from the balanced equation. Okay, that's not too bad, is it? So then, what will we have here? What will our equilibrium concentrations be? Well, let's start by saying, are we going to have numbers here? At least initially? Do I know what X is yet? No. But I can give me some information here. I'm going to kind of cut these in half. Not actually visually, but I'm just going to kind of use the top. Does that make sense? What I'm writing here, I'm going to write kind of small, because when I do know the numbers, I want to put them in here, because I'm going to be proud of them. But what will this number be? Well, whatever it is, we know that we started with and we know it's going down by So whatever this is, it's going to be 0.20 molar minus X. And then obviously we'll put the real number once we know it. What about this one here? Yeah, it's going to be 0.20 molar minus some number X, and that's going to equal, what's this going to be?
X.
Yeah, it's going to be 0 plus X, which is just X. And obviously we can put what that number is once we know it. What will this one be? 0 molar plus X, which just simplifies to X. Now, we've got to solve for X. How do we solve for X? Well, the last one was pretty easy. This one, not so much. This one's pretty tricky. But we're going to solve for X using our Keq equation. Does that make sense? We are going to have to substitute these into the Keq equation. Is that going to be fun? I mean, I suppose it depends on your definition of fun. I think it's going to be fun. What is our Keq equation? We said Keq equals what? Well, first of all, the question actually tells us what Keq equals. What does Keq equal as a number? Okay, so the first thing we can say is it's 0.83. But having said that, what does that equal? Well, it equals... What's it equal? Well, let's just... So the first thing it equals is the concentration of H2, right? Well, what's the concentration of H2? 0.20 molar minus X. And I'm going to give you permission. You know what we can do here? We can ignore units. Oh, shoot. Oh, no, what did I do? I failed. I have failed so miserably, and it makes me feel sad. You're totally right. What is it? Just X. Ooh, that was almost bad. Very sorry. And then next, we need to know the concentration of CO2, which is just Thank you for saving me from myself. I would have been real annoyed if I'd noticed that 3 minutes from now. And then what goes on the bottom? Well, we need the concentration of CO. And here, now that I'm not getting ahead of myself for a change, what's the concentration of CO? Oh, wow, that's like not even visible to you guys. How much?
0.20
Great. And I am going to give you permission to not put units and not worry about unhelpful zeros when you do these calculations, okay? Make your life a little easier. And what will be the concentration of H2O here? Very good. Okay, now, the first thing I would say is you can throw this into Desmos right like this, okay? And it's not a bad idea. I never would have taught this 5 years ago this way. I was such a purist. I was like, no, your algebra skills must be impeccable. But I've really changed gears where I think if you understand what we're doing here, then getting a little bit of algebra help is not gonna hurt anybody. But do you understand what we're doing here? We're saying we don't know what x is, but we know that at equilibrium, this value is going to be x, that value is going to be x. This value is going to be 0.2 minus however much it's lost. This value is going to be 0.2 minus however much it's lost. And at equilibrium, all of these have to multiply together to give us our Keq. And we looked up our Keq in a book. And when we looked our Keq up in a book, what did we get? 0.83. So all this has to equal that. So listen, I'm going to show you the algebra in a moment. But first, set it up. 0.3 equals, make a fraction, x times x, divided by 0.2 minus x times 0.2 minus x. And it will give you the only possible answer. How many possible answers are there? Just one. And you know what's beautiful? See this green line? This green line is what x equals. And I can just click it and I can see what x equals. But I do want to show you the algebra. Does that make sense? But before I show you the algebra, can we talk about how, imagine that you could just look at this and solve for x. In other words, you know, like when you get an equation, if I gave you this, you could tell me what x is, right? Just looking at that, what does x equal? 2. Is everyone comfortable with that? 3 times some number is 6, the number is 2, right? Imagine that you could look at this equation and do it just in your head instantly. Wouldn't that be nice? Let's imagine we've just done that. All right? Can we back up there? I want to go back and look at what we've done. We've taken the equation and we wrote a Keq expression. And we said that for this reaction, Keq is going to be the concentration of the products divided by the concentration of the reactants. And in this case, all of the exponents are 1, right? Then we said, well, we start off with 0.2 of this, 0.2 of that, and none of the products. And we said, well, this is going to go down by some number. And while that is going down, this is going to go up by some number. That's comfortable? So we said at equilibrium, this will be the original 0.20 minus however much we used. This will be the 0.20 minus however much we used. But this will be the positive of that number. However much of this we used, that's how much of this we get. And that's how much of that we get. Is that reasonably okay? Then we plugged those into this equation. And then, if we had magical superpowers that we could just do that in our head, we could look and say, y equals, oh, I screwed up. I could look and say, oh, look. Oh, I hate when this happens. Intersection. Why in God's name is it not giving me a value for that? Well, anyway, it looks like 9.5. Can we all see that? 0.095. So I can say, okay, using superpowers, x equals 0.095. We're going to go back and show you how to get that x. But I just want to say, imagine we didn't have to worry about getting x. If I knew x, then we could say, at equilibrium, how much H2 will I have? I'd have 0.095 molar. How much CO2 would I have? Very good. And how much H2O would I have? And that ends up being 1, 1, right? Actually, it just ends up being 1, 0. 2 sig figs, right? But I'm going to just put the 5 there. We'll deal with sig figs later. Actually, we're adding and subtracting, so never mind. That 5 matters. So there we go. And what about here? 0.105. Actually, we're adding and subtracting, so that 5 doesn't matter. But anyway, I'm not worried about sig figs right now. And that's how we would do it. Does that make sense? Now, can I ask, is there anyone whose algebra skills are such that they look at this and say, yeah, solving that's easy? No. Okay, can I walk you through it? Okay, first things first, you know what I hate? Fractions. So you see this bottom here? If they're divided right now, what's the opposite of dividing? Multiplying. So I'm going to multiply both sides by them. I'm going to multiply by 0.2 minus x, and again by 0.2 minus x. I want to do that in a different color so it's obvious where that comes from. Maybe I'll do it in green. And what I do to one side, I have to do to the other, 0.2 minus x and 0.2 minus x. And that means that will cancel with that will cancel with that. What will the next line of my algebra be? Well, this side's easy, just x times, okay, that was easy. And this side, I will still have the 0.83, but now next to it, I will have, okay, now we're going to have to expand. Expand, simplify. So this is easy. What's x times x? Okay, that was the easy one. What's 0.2 minus x times 0.2 minus x? Well, you can know your squaring rules, or you can FOIL, or you can just draw rainbows like I do till it works. What's 0.2 times 0.2? 0.04. What is 0.2 times negative x? Very good. What is negative x times 0.2? Again. And what's negative x times negative x? Positive x squared. Okay. Now here's the nice news. Something cancels. Because if I have an x squared on this side and on that side, if I want to get rid of this x squared, what can I do? The opposite of adding x squared is? And if I subtract x squared from one side, I have to subtract it from the other. So that's awfully nice. Don't you think? You don't? I do. Because that'll cancel and that'll cancel. What's my next line? Careful. Yeah, 0.2 minus another 0.2 is 0.
Can I just write 2 brackets 0 negative, or can I just write like minus 2 brackets 0.2x?
Yep, if you like.
Oh, or you can just use 0.4x.
Yep. Okay, and then I should move something to the other side. I hate negative signs, so what's the opposite of subtracting 0.4x? Nope, opposite of subtracting is? Adding. Very good. And what I do to one side, I do to the other. So now I've got 0.04 equals, very good. And now I think we're actually going to see that when I looked on the other page, on Desmos, I was seeing a bit of a rounding, but that's fine. Because what should my last step be? Divide out the 0.4. And when I do that, what do I get? X is equal to 0.1. So actually, my math gets even easier because these will be 0.10 molar 0.10 molar, 0.10 molar, and 0.10 molar. They all end up being the same. Now, that's not the only way to solve that, but it's the most straightforward way. There are easier ways, I guess. We also, of course, could have thrown it into Wolfram Alpha. But does that algebra feel like a push? Do we need some algebra practice? Okay. Tomorrow is just going to be pure algebra, right? We're just going to get some practice there. But again, to show you on Wolfram being our friend, if we had 0.83 being equal to x times x divided by 0.2 minus x times 0.2 minus x. And Wolfram even highlights your brackets so you know which one you've closed, which is really nice. Oh, shoot. I know why we got the wrong answer, guys. What did I just get rid of completely? Oh, I'm fired. Which is fine. So it's just been here this whole time. It's been here this whole time. Well, I guess it's not totally fine. In fact, you know what? I lied. Which also means we were right before. This is, see, and remember when I said, like, do you think your algebra is good enough? Maybe my algebra was the problem. Okay, so let's review where we were here. We had 0.83, and then in this bracket, we had 0.04, and then minus 0.4x plus x squared equals x squared. And we are going to have to do a quadratic. How do we feel about quadratics, team? Do you guys remember the quadratic equation? Like this, can I ask, like this feels like, whoo, way over our head? Okay, so again, that is just a function of like, you weren't in person for grade 10 and 11 math the way you'd like to be. I don't want you to stress about it. We're going to do fine. But we have to multiply 0.83 into all these. Okay. What's 4 times 0.83? Or 0.04 times 0.083? Anybody? I mean, it's going to be 32 plus 332. Cool. Minus what's 0.4 times 0.83? Very good. And plus 0.83 x squared equals x squared. All we did was expand that. That multiplied by that. That multiplied by that. And that multiplied by that. Okay, do you remember setting up quadratics? You always want it to be equal to 0. That's where you get a parabola and you find the roots, right? When it's equal to 0? Okay, so I'm going to have to take this x squared and get rid of it. So it's 0, so I'm going to have to subtract it. If I subtract x squared there, I also have to subtract x squared here. So we get 0.0332 minus 0.332x. And then this will be minus, is that going to be 0.17? Will it? Okay, cool. And then you're going to have to set up a quadratic equation. Do you remember the quadratic equation? X equals negative b plus or minus the square root of b squared minus 4ac all over 2a. Now listen, I'm going to tell you right now. You know where you should set that up? Do I want you doing this by hand? Not even a little bit. Not even a little bit, all right? This is a perfect case where you go like, let's set this up. Sorry? For what?
For 0.83 squared.
It's not squared. You're just multiplying it by x squared. That's 0.83 times x squared,
Oh,
which is just 0.83 x squared.
Bottom expression, it looks like it says, like, no, just, yeah, that one, it looks like it says 0.83.
Yeah, it is.
Yeah.
Yeah, it's just 0.83 times x squared. 0.83 times x squared is 0.83 x squared. Because the number in front of x squared here is 1. And 1 times 0.83 is 0.83. All right. And then if you want to set up a quadratic equation, just set it up like negative b plus the square root of b squared minus 4ac all over 2a. My advice would be, and then copy and paste that and do it with a minus. My advice would be, when you're doing chemistry that's going to have equilibrium stuff like this, build this before you do a single question. Does that make sense? Have a computer in front of you, build this, and then if you remember, the a is the value in front of the x squared, which in this case is negative 0.17. B is the number in front of the x, in this case negative 0.332. And C is the number without an x, 0.0332. And it will solve for the two possible values of x for you. We'll do this again tomorrow. Listen, guys, don't be discouraged, all right? You're going to get so much practice at this, you're going to be algebra wizards by the end of it. Wizards. Have a good one. Sorry? You're fine. Every question's the same.